Hello, I'll be talking about some maths. Yay! First, I'm going to talk about a vector project we did, and then I'm going to go through a proof for a differential equation. So I'm going to present the whole project, briefly explain what a vector is, the plane, which is also important, then get into what we did and how we did it, a bit, not too much, just the brief overview. So the project goal was to show that we understood how vectors bounced between surfaces, which are used for a whole bunch of different things. And my group decided to do this by building a maze and bouncing the vectors between a start point and an end goal. The start point is this point here, and the goal is a sphere in the end of the maze. We did a bit of a story around it. An alien is attacking Earth, and a secret agent has been sent to the mothership to destroy the alien leader. And he has to bounce his special bouncing bullet between the maze and destroy the evil sphere. So, first, what is a vector? A vector is a magnitude and a direction. It's very common to use it to describe it in a way very similar to a point where you have different values, because this effectively gives you a magnitude and a direction. If it's a normal two-coordinate system, it's y and x of a vector like this, but you don't need to do that. You could use it with a magnitude and an angle, a different kind of system. So it's how much are you going, how far, and in what direction is a very common. You can also use it with force in physics. How strong is the push, and in what direction is it pushing? And when you put different vectors together, you get a combination of them. So if we had a vector opposite of A, call it B, going this way, the sum of the vectors would be 0 if their magnitude is the same and directions are opposite. So vector, direction, and magnitude. A plane is what we use to build the maze. And it's something used in three-dimensional geometry. When you use a normal 2D coordinate system, you're actually working on a plane, and we just built planes in a 3D coordinate system. We used 3 points, but you can do it 2 points in a vector. It's simply a flat surface going in every direction forever, and it is only ever in 2 dimensions. Or it can I'm not sure, it can be in more dimensions, but you can build a 2D coordinate system on it. And we just built a whole bunch of planes and then restricted how far they went, because normally a plane doesn't really have limits. It's just a direction. But so we restricted them and built this wonderful maze. So the final thing I have to talk about is the vector bounce. When a vector hits a surface, you can do calculations about which direction it will go afterwards. And obviously, it's very complicated. I think it's basically impossible to do this in real life. I don't actually know, but I reckon it seems like it will be very hard. But in theory, it would predict, okay, if I shoot a bullet at that wall at that angle, it will go in that direction. Or in reverse, say a victim has been shot, and you can say the shooter stood here because the angle of the bullet on the wall would mean bounced in a certain way. So all you need is the ingoing vector and the angle it hits. Oh, excuse me, I'm a bit sniffly. I was saying you need the ingoing vector and the angle it hits the surface or the plane, and then you can calculate the outgoing vector. The actual calculation I'm not going to get into because this is just a brief overview, not really important. Well, it is important, but more advanced I'm going to get into this brief overview. These are final results. Remember, this is 3D. It's just easier to see from this angle. There is a wall here, so it can't just draw out the hole because there isn't one in reality. Just removed it for the picture. I was just interrupted by my by my sister. So the vector bounces between the surfaces, and there's a hole over here. You can't see it from this angle, and it hits the alien monster. Doing this by hand is basically impossible. It would take forever to figure out how you would get from here to here. So we wrote a computer program who did that, and the program just bounced vectors in random directions until it hit the queen, and put some limits on it. That would be no more than 15 bounces before the bullet. We said the bullet will fall apart after 15 bounces because it would be next to impossible to see what's going on if we didn't limit that. And then we just let the computer throw vectors out in random directions until it found a solution. We ended up finding two solutions, this one and this one, both very nice. So, on a totally unrelated note, I'm going to talk about second-order linear non-homogeneous differential equations. That's a mouthful to say. First, I'm going to explain what is a second-order non-homogeneous differential equation. Then I'm going to prove the general solution to that differential equation. So, the general form of the second-order non-homogeneous linear differential equation is this one. The second derivative of y plus p of x times the first derivative of y plus q of x times y equals g of x, where g is a non-zero function. And that's important because the homogeneous equation is basically the same except it equals 0. So if g was a zero function, if g equals 0, it would be homogeneous. So that's important. A second equation here, the homogeneous, is called the corresponding equation because tied together you need this one to solve this one. So equation 2 is a homogeneous differential equation corresponding to equation 1, the non-homogeneous equation. If y1 and bit y1 and bit y2 are both solutions to equation 1, then a solution to equation 2 is bit y1 minus bit y2. That means that we can equal y1 minus y2 to the general solution of the homogeneous differential equation, which is given as a fundamental set of solutions, little y1 and little y2. We put a bit different letters now, thinking about it, and two constants. This one down here. This is a different general solution. It is a general solution to equation 2. And I won't get into how you get this one. That's a different proof. I don't really have time for that. So it might not be obvious why y1 minus y2 equals this, or equals a solution to equation 2. So I'm going to explain that or prove it. By placing y1 minus y2 into equation 2. So we start by just inserting y1 and y2 into equation 2, get this. Then we remove the parentheses under this statement. And finally, we group y1 and y2 together, get this one down here. Now notice they both look very similar to something we've seen before, because both of these statements are in fact equal to equation 1. y1 and y2 are both solutions to equation 1, which means both of these are equal to g of x. So this statement is actually g of x minus g of x, which is obviously 0. Remember, if you place y1, place that with small y, replace small y, y1, that's a solution. Same with y2. So this is obviously true. If that is true, we can actually find the general solution. It's not that hard, the final part, because we can define y1, instead of having y1, we can have y of x, which is the general solution to equation 1, and have yp of x, which is just any particular solution to equation 1. And remember, they are both solutions to equation 1, which means this statement is true, as we proved that here, that if you have two solutions to equation 1, you can get the general solution to equation 2. So now we isolate the general solution to equation 1, y of x, and we find that the general solution of equation 1 is equal to the general solution of the corresponding equation minus a particular solution to equation 1. To summarize what we found, to find the general solution to a non-homogeneous second-order linear differential equation, you need a particular solution to the non-homogeneous second-order linear differential equations. God, that's hard to say. And the general solution to the corresponding homogeneous second-order linear differential equation. And now, I know I didn't explain how to get this. This is a different proof for different differential equations. You need something called a Wronskian to find a particular solution set, it's called. And I wanted more than that as the briefest overview you're going to get. So that was that. The end.